In this video, we're going to talk about projections, or Trefether and Ball call them projectors, but I personally don't use that language. It's projections. So definition, a projection is a linear transformation P such that if you apply the operation twice, it's the same as applying it once. So this is called a projection. The basic example that you should always have in mind, it's not the only example, but you'll see it has some important properties that we want to replicate, is a projection as a 3x3 matrix. By the way, a projection has to be a square matrix because in order to square it as an operator, as a function, it has to have the same number of rows as columns. Imagine the map from R3 to R3 that takes x, y, z and disposes of the z variable to project that point onto the xy plane. So as a picture, in our standard xyz coordinate system, if you have a vector here, its image clearly I need a new marker. XYZ goes to XY0 by throwing away the z component. As you might imagine, the notion of a projection is tied to the idea of vector projection, of projecting one vector onto another, which we'll come to in just a moment, the orthogonal projection. Before we proceed, let me point out a neat fact. If you have a vector v and you apply a projection to it, well, let's just call that PV. Now, what if you take v and you ask what part of v was not projected? So consider v minus PV. In this picture, the orange vector xyz is v, and the red vector xy0 is PV. So what vector is v minus PV? Well, it's the thing you would add to PV to obtain v, and that is this right here. We can call that I minus P times V. So whenever you have a projection P, there's another map called I minus P, which is the part that's left behind. So the vector xyz has the part the projection sees and the part the projection discards. And I minus P is the part that discards. The part that's discarded. Now, of course, PV plus I minus PV is equal to I, obviously. I'll write that down just as a reminder. And of course, the red vector plus the black vector is the orange vector. But here's another simple fact, which is very important. If you look at I minus P and you square it, P squared is equal to P by definition. So, I minus P is also a projection. So for any projection, you can think of it as there's some subspace, namely the image of P, which you are projecting onto, and some other subspace, namely the image of I minus P, which you are projecting away from. So in this case, we have P takes xyz to xy0, and I minus P takes xyz to 0, 0, z. Here's another neat fact about projections. Well, a projection it can be represented as a square matrix or as a homomorphism of a vector space. We can ask, what are the eigenvalues? Of such a matrix? Well, suppose we have an eigenvector. So suppose we have a vector v where PV is lambda V, and of course V is non-zero as it's an eigenvector. We never consider 0 to be an eigenvector. Applying P to this equation one more time, we see that P squared V is P lambda V, which is of course lambda PV by linearity. The left-hand side is PV because P is a projection, and the right-hand side is, well, PV is lambda V by assumptions. This is lambda squared V, and this side is lambda V. So overall we have the equation lambda V equals lambda squared V. In other words, lambda minus lambda squared, V is equal to 0. So now we ask, what complex numbers have the property that lambda equals lambda squared? Right? V is not 0, so the only way this can be 0, the 0 vector, is if the coefficient is 0. So what numbers have this property? Only 2 of them, lambda equals 1 or 0. So a projection has only two possible eigenvalues, 1 or 0.